Welcome to Space Drift. Please subscribe and hit the bell icon for more breaking updates. Since its historic launch on Christmas Day 2021, the James Webb Space Telescope has ushered in a new era of cosmic discovery, fundamentally transforming our understanding of the universe and our place within it. This marvel of engineering represents decades of international collaboration, ambition, and ingenuity, all culminating in a single, breathtaking mission. Its iconic gold-plated mirror, spanning over 21 feet and stationed nearly 1,000,000 miles from Earth, acts as a time machine. Peering back to the universe's earliest days, Webb reveals cosmic secrets that have remained hidden for billions of years, capturing the faint light from the first galaxies and allowing us to witness the birth of stars and the formation of cosmic structures. Unlike its predecessor, the Hubble Space Telescope, Webb's powerful infrared vision slices through dense clouds of cosmic dust, exposing star nurseries, the atmospheres of distant exoplanets, and the intricate details of nebulae with unprecedented clarity. This ability to see the invisible has opened up entire new realms of exploration, revealing phenomena that were once beyond our reach. The telescope's flawless deployment, a feat many thought impossible, and its breathtaking first images have silenced skeptics around the world. Webb has delivered data that is not only scientifically invaluable but also visually stunning, inspiring awe and wonder in both scientists and the public alike. Webb's advanced instruments such as NIRSpec and MIRI dissect the faintest starlight, revealing the chemical composition, temperature and motion of distant worlds and galaxies. These tools allow astronomers to study the atmospheres of exoplanets, search for signs of life and unravel the mysteries of planetary formation. Each new observation is a potential breakthrough, shifting our cosmic perspective and challenging what we thought we knew about the universe. Webb's discoveries are rewriting textbooks and sparking new questions about the origins of stars, planets, and even life itself. And now, in the midst of this scientific revolution, Webb has captured one of the most dramatic events ever witnessed in astronomy, a violent, awe-inspiring glimpse into the birth of planets, forever changing how we see our cosmic neighborhood. 1,800 light-years away, the star ASASN 21QJ became the scene of a cosmic catastrophe. Ground-based telescopes first noticed the star dimming in 2021, but archival infrared data revealed a prior brightening, evidence of a massive collision. Two Neptune-sized ice giants had smashed together, releasing a burst of energy and a cloud of dust that blocked the star's light. For the first time, astronomers caught both the before and after of a planetary collision. Webb's infrared eye then targeted ASASN 21QJ, seeking the glowing embers of the newly formed world. This was no longer theory. Webb directly observed the aftermath of planetary birth through violence. The event offers a real-time laboratory for studying how planetary systems evolve through chaos and destruction. The universe's capacity for both creation and destruction has never been so vividly displayed. The ASASN 21QJ collision is the first direct confirmation of the giant impact hypothesis of planet formation. For decades, astronomers have theorized that planets are shaped by violent catastrophic impacts, but until now, we had only indirect evidence. This event is a breakthrough, offering a front-row seat to the drama of planetary birth and destruction. Instead of a gentle process, planet building is a chaotic demolition derby, with protoplanets colliding and merging over millions of years. These collisions are not rare accidents, they are the rule, not the exception, in the early lives of solar systems. Each impact can completely transform a planet's destiny, altering its size, composition, and even its orbit. Webb's data lets astronomers test these theories with real evidence, showing that even large planets can be reshaped by cataclysmic impacts. The telescope's powerful infrared vision reveals the heat and debris left behind, painting a vivid picture of these cosmic collisions as they unfold. This helps explain the wild diversity of exoplanet systems, hot Jupiters, eccentric orbits, and more. The chaos of collisions sculpts planetary systems into the strange and varied architectures we observe today, far beyond what we once imagined. Now, astronomers can search for similar events, using the telltale signs of infrared brightening and visible dimming. These signals act as cosmic fingerprints, allowing scientists to identify and study planetary impacts across the galaxy. A population of post-impact systems could reveal how debris clouds disperse and new planets cool. By tracking these changes over time, astronomers can piece together the timeline of planet formation and the aftermath of these colossal events. Observing such events in real time puts our own solar system's violent history into a broader context, It shows that the chaos that shaped Earth and its neighbors is a universal story, repeated countless times across the cosmos. The Earth-Moon system, likely born from a giant impact, is no longer just a theory. It's part of a cosmic pattern. Our planet's history is echoed in the stories of countless worlds, each forged in fire and collision. The collision at Sassen 21 QJ marks the beginning of turning speculation into science. With every new discovery, we come closer to understanding the true nature of planet formation and our own place in the universe. Webb's follow-up observations of Sassen 21 QJ brought surprises. The post-impact planet was cooling much faster than models predicted. The light from the system behaved erratically, defying expectations of a simple cooling trend. This suggests complex processes within the debris cloud, perhaps chemistry, or multiple fragments interacting. Such puzzles are the heart of scientific progress. Unexpected results force us to rethink what we know. Webb's exquisite data is challenging theorists to refine their models of post-impact physics. More observing time is already scheduled, as astronomers race to unravel the mysteries of this newborn world. The messiness of discovery is where the most profound advances are made. Wrestling with these cosmic puzzles pushes our understanding to new frontiers. While distant worlds collide in the far reaches of the universe, Webb has also revolutionized our view of the solar system's outer reaches, bringing the mysterious frontier of our own cosmic neighborhood into sharp focus. Its extraordinary sensitivity has unlocked the secrets of the Kuiper Belt, a vast region beyond Neptune filled with icy bodies and ancient debris. Webb's instruments have revealed the chemistry of trans-Neptunian objects, frozen relics left over from the solar system's birth, offering a window into the earliest days of planetary formation. For the first time, Webb captured direct images and detailed spectra of Neptune's auroras, glowing bands of light that dance across the planet's atmosphere. These auroras are found at mid-latitudes, a result of Neptune's dramatically tilted magnetic field, which creates unique and unpredictable patterns. The telescope also discovered that Neptune's upper atmosphere has cooled dramatically since the Voyager 2 flyby in 1989, a surprising change that challenges our understanding of planetary weather and climate. These findings show that Neptune is far more dynamic and changeable than scientists once believed, with shifting temperatures and evolving weather patterns. Webb's ongoing survey of trans-Neptunian objects has cataloged over 75 distant worlds so far, each with its own unique story. The telescope has revealed surfaces rich in water ice, carbon dioxide, and other exotic ices, painting a complex picture of the outer solar system's composition. Even more exciting, Webb has detected complex organics, the building blocks of life, on some of these remote objects, hinting at the chemical richness of our solar system's frontier. This ongoing chemical census is rewriting our understanding of the solar system's architecture and history, revealing new clues about how planets and moons formed and evolved. In a sense, Webb is conducting cosmic archaeology, digging through layers of time and space to uncover the hidden story of our origins. With every new discovery, Webb is helping us piece together the epic tale of our planetary home, showing that even in our own backyard, the universe is full of surprises. Webb's detailed survey revealed that TNOs fall into three distinct chemical groups: bowl type, double dip, and cliff. Bowl types are rich in water ice, likely formed closer to the sun and later scattered outward. Double dip and cliff types contain more complex organics and volatiles, with cliff objects representing the most pristine, untouched remnants of the outer solar nebula. The correlation between orbit and chemistry confirms theories of planetary migration and solar system evolution. Webb's data provides a chemical map of the primordial solar system, showing how different regions contributed to today's architecture. The Kuiper Belt's diversity is a fossil record of our solar system's turbulent youth. From faint, distant light, Webb has delivered profound insights into our origins. The discoveries of planetary collisions and TNO chemistry are just the beginning for Webb. Upcoming observations of SN 21 QJ aim to solve the mysteries of rapid cooling and erratic behavior. Astronomers will now systematically search for more planetary collisions, building a comparative sample to refine our understanding. The TNO survey will expand to extreme objects like Sedna, probing the solar system's outermost edges. Webb will also study binary TNOs and monitor Neptune's auroras over a full solar cycle. Each new observation adds to the grand puzzle of planetary formation and evolution. Webb's greatest discoveries may still lie ahead, challenging our theories and reshaping our cosmic perspective. The golden eye has opened, and the age of discovery has just begun.